Mackenzie's like joining.
All right, let's open up to page 149. We're going to take a look at our next section today. We're going to look at two new graphical characteristics or properties today. We are continuing to add to our list. Yeah. Say it again. After break. Okay. After break. So schedule-wise, might be a good time to go over that. Today and tomorrow, we're going to take a look at this section. And then Friday and Monday, we'll take a look at the last section of the unit, which means Tuesday is your review day. And actually Wednesday, the half day, we're going to be in here for like 15 or 20 minutes together. You can use that as a review time too. So that means the day we come back from break is test day and homework is due. So you do have quite a bit of time to work on your homework over break and study. Okay, so I know it's not the most opportune timing, but unfortunately that's how it's working out. 2 days. Yep, so we come back on a Tuesday, so it'll be Tuesday, Wednesday. All right, in this section, we're going to take a look at two more graphical characteristics we've been talking about a lot so far. We have domain and range, increasing, decreasing, above x-axis, below x-axis. Have we done other ones? Those are the main ones so far. Okay, we're going to continue to add to the list. We've done x-intercepts and multiplicities. Okay, we're going to review those a little bit on this first page, and then we're going to introduce two new ones today. So based on the way this graph of f of x looks, can we describe or name the type of polynomial that it is, and perhaps give a reason? Yeah. How'd you know? Okay, so 1 plus 2 gives you 3. So this is a cubic graph, and we'll say the multiplicities add to 3. What about g of x? The next one, can we name it? Maybe you can tell based off the shape, too, if you're kind of familiar with these polynomial functions. Cubic graphs always have that S shape to them. This one kind of looks like a W, bless you. Maybe look at multiplicities. What do you think, Elsie? Quartic, okay, so power of 4. How'd you know? Okay, so looking at the x-intercepts, we can label the multiplicities based on how they behave at the x-intercept. Notice how we go straight through or we bounce. So the multiplicities add to 4 in this example. What about h of x? Yeah? Quintic. So x to the 5th. Can you identify the multiplicities?
There are 2 in multiplicity of 2 and then 1 in multiplicity of 1.
All right, so the ones that bounce have the multiplicity of 2, and then we go straight through at the origin, so there's a multiplicity of 1. So the multiplicities add to 5. Looks good. So based off the way the graph looks, we can find those x-intercepts and their multiplicities, and then we're going to know the type of function that we're dealing with, or at least the highest power, 3, 4, 5, something like that. So let's go ahead and take a look at p of x at the bottom, and we're going to review some other graphical characteristics that we've discussed so far this year. We have domain and range, left and right end behavior. We saw that a little bit in the last section. And then we'll take a look at above x-axis, below x-axis, increasing, decreasing, kind of those ones. What about the domain of this? This seems to be the same graph as g of x above. So what about the graph of this quartic function? How far left and right would this graph go? Can we drag our pencil? Any holes or asymptotes or missing pieces that we have to be concerned with? No. All right, so all real numbers, negative infinity, positive infinity. What about the range? Drag your pencil, low to high. Good, Lainey?
-4 to infinity.
Okay. Can you do symbols? There we go. All right, so we start at -4, and we physically touch our graph at that y value, and then with the arrows going up, we can go towards positive infinity. Looks good. Let's do left and right end behavior. So when we look at the very ends of the graph, we're trying to determine what does the graph do. Does it go up? Does it go down? Maybe it does something else. So for left end behavior, we're going to go ahead and write our analysis mathematically. We're going to use math notations. So to the left is signifying that the x's get very, very negative. So we're going to say as x gets very, very negative, what do the y values do? So the further this graph goes to the left, which way does it travel? To the left and up. Okay, so the y values would approach positive infinity. So that's our left end behavior. If we do the right end behavior, the x values are getting very, very positive. So as the graph goes to the right, what other direction is it traveling? To the right and up. Okay, so the y's would approach positive infinity as well. All right. What about the intervals where p of x is less than 0? Can we think about what we should be identifying? What should we be looking for? See pencils moving. What are we writing? And it might be stick time. All right. Oh, if I can find our sticks. Hold on. Here we go.
All right, I'll answer it.
Go, Travis.
Okay. So we have, all of this is in parentheses.
Okay, go ahead.
We have -3 to 0, and
Mhm.
then a u,
Okay.
of course it's still in parentheses, and then a 0 to 3.
Okay, and then what is that, or what are those intervals identifying, specifically about this graph? These are the intervals where what? Yeah?
The points are below the
Below x-axis. Okay, so graphically it seems like it's below the x-axis all the way through from -3 to +3, but we cannot include the x-intercepts because those are on the x-axis. We'll have to skip over -3, 0, and 3. So that's why Travis used parentheses. Looks good. What about if p of x is greater than 0? Kind of similar question, but where are we looking now? Good, Julia? The above x-axis. Okay, so graphically, those are kind of the regions that we didn't use previously. So that would be this top section and the other top section. Looks like negative infinity to -3, and then 3 to infinity. All right, one last review characteristic, increasing and decreasing. So if you were to physically walk along the path of this graph, where would you be walking up? Where would you be walking down? Okay, can we list those intervals? Let's go up first. Can we find them? Robbie, do you have an idea where we're going up or decreasing if you'd prefer to do that one?
Increasing or going up from, these are in parentheses.
Okay.
-2 to 0, and then a U, and then 2 to infinity.
I like it. Okay, so 2 to 0, we have that little section going up, and then 2 to infinity, that section going up. Looks good. What about decreasing, where you'd be going down? Good, Julia?
Parentheses, negative infinity to -2, and then another parentheses, U, and then parentheses, 0 to 2.
All right, so it's kind of the other two sections going down here and going down here. Looks good. All right, good review. Okay, we're going to introduce two more graphical characteristics that we're going to identify today. The first set are maxes and mins. I'm pretty sure we've seen these before. Maybe not formally defined them, and that's what we're going to do today. But we're just basically looking for high points and low points. So our first vocabulary term is a relative maximum. Relative just means in relation to points around the high point. How is the graph behaving? So we're not really looking at the graph as a whole. We're just looking at a little section of the graph, relative like to the points around it. So formally, a definition we can use is a relative max is a point on the graph where the graph changes, increasing to decreasing. So this is why we had to practice identifying increasing intervals and decreasing intervals. If we can find where that changes, then we can locate a maximum or a minimum, okay, depending on the direction you're going. So in the first graph, can we identify a point, okay, an x and a y coordinate, where the graph changes from going up to going down? Increasing to decreasing. Yeah? 1, 4. Okay, notice how in relation to this point, around that point, we are going up before it and down afterwards. So we're not looking at the whole graph. We're just looking at that particular little section. So 1, 4. Definitely. Any other ones? You can't have more than one maximum or minimum, as long as it fits this definition, a point where it changes, increasing to decreasing. I say we're pretty good for that one. What about the second graph? Can we identify a point where the graph changes, increasing to decreasing? You have an idea, Lainey?
-2, 6.
Okay. So in relation to that point, we go up before it and down afterwards. That fits our definition. Is there another point where it changes? Go to Olivia. 2, 0. You go up before, down after. So basically, for these relative maximums, we're looking for high points like the top of a hill, the top of a mountain, the top of a crest, okay? That type of structure to it. Relative minimum is very similar. We're going to have a point where the graph changes, in this case, decreasing to increasing. Looking at the first example, can we find a point that fits that definition? If you were to trace it left to right, where would your pencil change from going down to going up? Go to Olivia. 3, 0. All right, so in relation to that point, we decrease before, increase after. Looks good. I think that's the only one. What about the W shape? The quartic function? Can we find some relative minimums? What are we thinking? Negative 2 comma negative 4, okay. Decrease to increase looks good. There's another one. 2 comma negative 4, all right, somewhere right there. Decrease to increase. Looks good. All right, so relative max, relative min, we're looking for points, okay, physical x and y coordinates. What we can use to lead in, or this can lead us rather, into a new vocabulary term called an absolute maximum or minimum. So absolute is like the highest or the lowest, not just any high point or low point on your graph. We're looking for the highest or the lowest. And what's a little different with these is we're not really looking for a physical point anymore. We're just looking for a height. So we're looking for the absolute lowest height, the absolute highest height, whatever the case is. And if we're dealing with a height, normally that's a y value. How far up or down are you? So for an absolute minimum, we want to find the lowest y value the graph reaches. Taking a look at the first graph, can we find the lowest height the graph reaches? Idea, Carter? Negative infinity, okay, because of the arrow, it is going down. Are you going to reach negative infinity though? Can you ever physically get there? No. Okay, so the lowest, in this case, we would say we don't have an absolute minimum because we never ever reach a lowest height, okay, because it's going down forever. So we can just say none in this case. I'd understand if you said negative infinity, but I just want you to be aware, like on a quiz or a test, it'll probably say none because you don't physically reach that. Okay, but I can understand why you would say that. What about the second graph? The lowest height the graph reaches. Yeah? Negative 3, right there. All right, so y equals negative 3 is our absolute minimum value, okay, the lowest height. On the next page, we'll tackle the other option. Okay, what if we have an absolute max? This time we want the highest y value a graph reaches. What about our first example? Is there a highest height? 6, looks good. So y equals 6 is our absolute maximum value. What about the second graph? We're shaking our heads no. Good. Notice how this graph will go up forever, so there's actually no limit to that. Okay, no highest height. So we'll just go ahead and say none. All right, so new characteristics. We can talk about maxes and mins. Relative maxes and mins are the points, like any high point, any low point, but the absolute maxes and mins are the heights, like the highest height, the lowest height. So the wording is very similar because you have maxes and mins, but you have different types. You can have relative, you can have absolute. Relative are points, absolutes are y values. Okay, difference between the two. Our next characteristic we're going to talk about is a point of inflection. And I'm pretty sure this is going to be new to us. I don't think we've ever seen this term before. By definition, a point of inflection is a point on the graph where the concavity, maybe that would be a new word for us too, the concavity, meaning the curvature of the graph changes. Okay, And I'll go ahead and use the first graph at the top as an example. I'm pretty sure we've heard the word concave before, maybe in your science classes, like concave lens, convex lens. Okay, it's about the curvature of the lens. We're looking at the curvature of a graph now. So, for instance, the graph at the top, if you were to trace it from left to right, notice how when you initially trace it, you start to have kind of this upside down parabola curve. Okay, this is what's called concave down. The curvature is pointing downwards. But if I were to continue to trace it, notice how I'll eventually get to kind of a regular parabola shape. This is what we call concave up. And if I continue to trace it, notice how I'll get another concave down section. Okay, it looks like an upside down U. So if we're changing the curvature, we're going from pointing kind of down to pointing up, there must be some point where the curvature changes. And that's what's called a point of inflection. Okay, where the curvature changes from going up to going down. And there are 3 places graphically where this point of inflection can occur. We'll go over the 3 of them, and then we'll practice to make sure that we're okay with identifying those. So 3 places. They're not too difficult to remember, but we're just going to go ahead and make sure that we're all on the same page. One place where the curvature of a graph can change is where you have a multiplicity. If I can spell, multiplicity of 3. If you were to draw an example of an x-intercept that had a multiplicity of 3, okay, maybe we'll say this is the x-axis. Here's our x-intercept. Multiplicity of 3 is level, okay, as it goes through. And if you look at it, notice how the left-hand side kind of looks like an upside down parabola, but immediately after the x-intercept, it looks like a regular parabola. So you have that change in curvature. We go from concave down to concave up. So since we're going through levelly, okay, it kind of flattens out, that's what's creating the curvature change. Okay, that's not the case if we had a multiplicity of 1, because if it's a straight line, there's no curve to it. Okay, so there's no change. So multiplicity of 3 is one place where we can have a point of inflection. Another point is approximately the midpoint of a max and min. So what I mean by that is if you take a look at the graph at the top that I have in blue and red, notice how we have a maximum at the very top and then a relative minimum there at the bottom. Notice how this point of inflection that we roughly found is in the middle of the 2. Do you see how it's about in the middle? That's another spot where we can change concavity. So if we can identify where we have relative maxes and mins, okay, which we just practiced, by the way, we can figure out where the middle of that is, okay, by doing a little calculation or a little thinking. So the midpoint of a max and a min, okay, is another spot where the curvature can change. I think we're okay with these 2. The third place is kind of a merger of these 2 possibilities. So the last one, kind of the more difficult one for students to remember, is approximately the midpoint of a multiplicity of 3 and the closest max or min. And we'll see an example of that so it can kind of sink in. All right, I'm going to scoot this up a little bit so we can take a look at some some of the graphs at the bottom. All right, looking at our first example here, I think it's actually the same graph as the very top one. So we kind of have this visual already done. We're going to try to find the points of inflection. So going through our three options, okay, let's see where we can find these. Based off this graph, do you have a multiplicity of 3 anywhere? Doesn't look like it, okay? So we can rule off that first option. The second one, do we have any maxes or mins on this graph? Any high points or low points? Definitely, okay? So maybe we can figure out the middle of those points. So here's a relative maximum. We'll label the point -2, 6. And right after that maximum, we have a relative minimum. We'll say that's roughly 1, -1. So if we can identify a max and a min that are consecutive, okay, right next to each other if you were to go left or right, we want to try to find the middle of these 2 points. So we got to try to find the middle x value and the middle y value. Notice how the x's are -2 and 1. So on a number line, can you think about what would be in the exact middle of -2 and 1? Maybe you actually want to draw one to help you out. What's in the exact middle of -2 and 1? We can go 1 this way and 1 this way, and we're not in the middle yet. So it looks like we have to go 1/2 and 1/2 to get in the middle. Okay, so that would be -1/2. So that's our x value for the midpoint. Can we think about what's in the middle of 6 and -1 if you drew a number line? Two and a half. Good. Okay, so graphically, let's see if we can plot this point. -1/2, 2.5. Again, it's an approximation. Okay, roughly somewhere right there. Can we identify another point of inflection? Do we have another max and min that are right next to each other? Or consecutive at least? We can do the previous minimum, and then it looks like we have a maximum pretty close to that. So we'll have 1, -1 and 2, 0. Can we find the middle of those? In the middle of 1 and 2, 1.5. In the middle of -1 and 0, -1/2. Okay, so roughly 1.5, -1/2, somewhere right there. All right, so we ruled out any multiplicity of 3. We definitely had maxes and mins. And notice how if you rule out a multiplicity of 3, there's no way you would have the third option because that involves a multiplicity of 3. So our only case in this particular graph was this max and min midpoint. So if you were to label this graph, these points that we found are where the concavity changes. So initially, the curvature is down. Then we hit the point of inflection, so that means it must be concave up. And then we reach the other point of inflection, which means it's going to change to concave down again. So we're looking for these points on the graph where the curvature is going to change from up to down or down to up, okay, depending on what the graph looks like. All right, let's go ahead and try the next one. Rolling through our options, do we have a multiplicity of 3 anywhere? No. So if we rule out 1, we automatically rule out option 3. Do we have any maxes or mins? High points and low points? Definitely. All right, so we have a high point, a maximum at 1, 4, and we have a low point at 3, 0. We got to find the middle of those points. In the middle of 1 and 3, 2. In the middle of 4 and 0, 2. All right, so roughly on the graph, 2, 2, that's where the curvature changes. So it looks like we're concave down, and then we reach the point of inflection, so we change to concave up. Now we only had one set of maxes and mins, so we'll only have one point of inflection. We doing okay so far? Okay, we'll go ahead and try the last one. Do we have a multiplicity of 3 anywhere? Notice how we cross levelly. Okay, so we do have a point of inflection at -2, 0. We'll count that. Do we have a pair of maxes and mins? We have a minimum. Do we have a maximum somewhere? A high point? No. Okay, so we can rule out number 2. Now, we got to take a look at 3 because we said we had a multiplicity of 3. Maybe we can find the closest max or min, okay, which looks like to be this minimum here. And we're going to find the midpoint of these values. So we'll take -2, 0 and the minimum of 1, -6, and we'll try to find the middle of those. What's in the middle of -2 and 1? Oh, did I miss it? -5. Sorry. So we find the middle of -2 and 1. -0.5. Okay? What about the middle of 0 and -5? -2.5. Okay, so roughly, approximately, if we graph it, somewhere right there, okay, there's another point of inflection. So if we trace the graph, it looks like we are concave up first. We reach a point of inflection, so the concavity changes. It must be concave down now. And then we reach another point of inflection, so it must change to concave up. Notice how the first piece looks like a regular parabola, the middle piece looks like an upside down parabola, and then the last piece looks like a regular parabola. So we're analyzing the curvature of the graph. We doing okay? Yeah? Okay. We'll stop there for today, and we're going to bring all these different characteristics together tomorrow.